So we're going to work with something known as the tangent ratio. We'll write out how it's commonly written. So it's usually written as tan, and then you use this variable called theta as the placeholder for the variable. So this is an unknown, and it is equal to the opposite over the adjacent. So we got to do a whole bunch of defining things here. What on earth do they mean by opposite? What do they mean by adjacent? This ratio is something that holds up in triangles, and particularly a right angle triangle for what we're doing. Okay, the tangent ratio, and just like if you're familiar with sine ratio or cosine, these work specifically with right angle triangles. So we have a right angle triangle, so that is our first check mark to say, hey, we can use this. A common way of writing tan theta is also like this. They'll say tan theta is equal to the opposite over adjacent. They call it TOA as a way of remembering it because they'll have this little acronym called SOHCAHTOA to remember, okay? So if we know something is 90 degrees in a triangle, that's a known angle, we're then referring to, whenever we use these ratios, one of the other two angles. We're not talking about the 90-degree angle. So we're either working with this one, we'll call this A, or it could be B, okay? And we'll call the last one here, the 90-degree one, we'll call that C in this case. So depending on what what angle we're referring to, it changes what is known as the opposite side of the triangle or the adjacent side of the triangle. So we have to get used to setting that piece up. So for instance, and in this case, theta is a placeholder for an angle. This could be angle A. So I could technically replace theta with A. All this is a variable. It's a funny one. We're not used to seeing it yet. It's a Greek letter they use. I've maybe showed you before. I can use anything to represent a variable. I could literally have this as tan happy face. And happy face is just a placeholder for some unknown number that we're using. It's just really common in mathematics if we're referring to angles or something known as radians, which you'll get into in a couple later, many years from now. We use theta. It's just the common placeholder in mathematics for it. So tan theta, in our case, is referring to the degrees of some angle here. And in this case, we've called it A, okay? So what I'll say is I'll call this one theta. We'll say angle A is theta in this case. That way we can set this up. So if we were trying to set this up, I want to have this kind of part probably memorized, unless they're giving it to you as a formula. I want to know that tan of whatever that angle is, and we'll call that angle theta in this case, and remember that's technically A we're referring to, is equal to the opposite side of the triangle. So we have to get used to naming this. We'll go opposite, we'll put in green, and we'll put adjacent in blue. What we need to do is set up our triangle to be able to use this as a formula to help us solve parts of this. So if A is what I've called theta, that then means the opposite side of the triangle is directly across. It's the side length that this angle is not touching. So this would be the opposite side of the triangle for this. So we'll call it O in this case. Adjacent actually refers to the side it's touching, but is not the hypotenuse. So in angle A, if I'm creating an angle, I have two sides. There's two sides of the triangle touching, but one of them, assuming we're not working with the 90, which we never are, one of them's the hypotenuse. So think of it like the default for that side is always called the hypotenuse, and that's always opposite of a right angle. Okay, so this is our hypotenuse.
It's the longest one.
It's the longest side. That's another way of remembering it. Which then means, by default, if I know what the hypotenuse is and I know what the opposite is, I can just aim and name the third one. We know that this will be the adjacent side, okay?
Yeah.
So this is adjacent. If we have some numbers, we can use that to work out the rest of this piece. We're going to leave it at that for now because I want to show you what if we were referring to the other angle in the triangle. I want you to see how things change. I want that to be black so the colors are the same. Here we go. So we got this. We're going to use the exact same triangle. I'm going to try to set it up so it looks about the same. We have A, we have B, and we have C. Okay. Let's say we're referring to B. Commonly, we'll use theta again. One of the problems with doing that in lower level mathematics is we end up using the same variable to represent two different angles, and that can sometimes get confusing. You may notice in a textbook, if they ever refer to two angles of the same triangle, I'm not sure they'll do it here, they'll use another Greek letter variable. They really like using Greek letters to represent angles. And sometimes they'll use this Greek letter. It looks like a giant B. It's just known as beta. Okay? But what's important to know is that it's referring to an angle. And in this case, it's referring to the other angle. So I can, just like we said, we could say happy face if we wanted. If I was to say tan, instead of using theta, they've called this angle beta. And again, we could have used anything. Tan, this one could have been happy face. This guy could have been angry face. Like anything we want to represent the variable is fine. Okay. What's important for this is same idea. We're doing opposite over adjacent. What do we use? Blue. But in this case, those change. The hypotenuse never changes. It's always opposite of this right angle. Pretty easy. We're down to 2. We already named one of the 3 sides. We just got to name the other one. Well, because we're referring to B here, or beta in this case, but angle B, my opposite changes. My opposite is now this side of the triangle. Okay, which then means my adjacent by default must be this side of the triangle. And what's important to notice here is that it's the exact same triangle we used before. This is the exact same one. But depending on which angle we're referring to, the opposite and adjacent sides change, which is a really important piece. Because if we're going to use this formula, we need to make sure that we can tell which is the opposite and which is the adjacent. Otherwise, when we put things in, we're going to end up solving for the wrong angles of a formula. Okay, so let's take this exact same triangle again, and I'm going to, hopefully these ratios work. Let me see quickly in my head. Yeah, they'll work. I'm going to build the same triangle, and I'm going to actually give it some side lengths here. So we got the same triangle, but this time we got our 90. Let's say that angle A in this case, we're going to say that this is an unknown angle. Okay, I'm going to say that we called it theta before. It's unknown. We don't know what this angle is. But we do have some measurements. I got this. We're going to say that this is about 10 meters and this is 5 meters. Why not? Okay. I don't know the hypotenuse, or at least they haven't given it to me yet, which is okay. In a triangle, as long as you have 3 pieces of information, you can solve for everything else in that triangle. I have 2 side lengths. Do you happen to know what the 3rd piece of information I have about this triangle is?
The hypotenuse.
I don't know the hypotenuse.
You can like solve it.
Absolutely.
Yeah.
I can solve for it. But there's actually another thing they've given us. It's not so obvious, but we've used a symbol to represent it in the triangle.
The 90 degrees.
90 degrees. They've actually given us. So right away, you can check off for box here. We go 1, 2, 3. I got 3 pieces of info, therefore I can start solving, okay? And that 90 is what allows us to know that, I can use the hypotenuse by using Pythagorean's theorem, right? Let's go to this A. I want to solve for A. What am I going to use? Well, I don't have the hypotenuse. If I know sine and cos, it turns out I have to use those as the ratio. I have to use a hypotenuse, so I'll quickly write it up here. Sine is known as the opposite over the hypotenuse, so I don't have an hypotenuse. Cos is known as the adjacent over the hypotenuse. I don't have the hypotenuse. So by default, we have 10. Hello, mister. And we're going to set it up. I'm going to write that a little nicer. Tan theta is equal to opposite over adjacent. Well, if I look at my A, and from my previous triangle, if we look above, the opposite here is that 10 meters. Great. We have an opposite. And the adjacent is this 5 meters. Great. I have the adjacent. Oh, I wrote 5. I didn't mean to do that. I just wanted a check mark. Good. So I have 2 of the 3 pieces needed. The angle is what I'm trying to solve for. So I'm going to say tan theta is equal to, in this case, 10 is our opposite. So we'll write it in green here. And 5 is our adjacent. So it turns out that tan theta, this is a ratio, right? Tan theta is equal to a ratio of 2, or 2 over 1 if you really want to write it like a ratio, okay? Does that solve my angle? Not yet. In order to solve for the angle, I have to find the inverse of this function. So usually what they'll say is they bring tan to the other side and it looks different. You're really using a function which you guys haven't talked too much about. So in terms of your algebra, you just have to kind of remember that if I want to solve for this part, which is the angle, I can leave it alone on one side of the equation. And when I bring tan over, for not the best way to describe it, but we'll say when we bring tan over, we're taking the tan inverse of that same number. Okay? And let's see if I got a nice calculator we can bring up here. And now it's been sure. Let's go here. Most scientific calculator. Amazing. So I got our scientific calculator here. And if I go into the functions button, you'll see it already has tan, but I actually need the inverse of tan. And when I click that, I get this. Tan looks like it's the power of -1, but it has a set of brackets, and that's the argument we're going to put in. So we call tan 2. Turns out, there we go, we have it. Tan inverse of 2 gives us an angle, because we are in degrees on this calculator. You can see it's written in degrees there. That's another thing you got to check, just to make sure you're in degrees. It's 63.4, roughly. Oops, that's not what I wanted. Oh my gosh, where'd it go? Oh, here it is. Theta is equal to 63.4 degrees. Okay. What about the other one? What if it was this, and we're trying to solve for angle B? Remember we called that, we had another Greek letter. It looks like a B anyways. We'll call it beta. Tan of some angle, in this case we use that Greek letter again, B, to represent it, or beta I should say, is still over the opposite over the adjacent, but the opposite changed. When I refer to angle B, my opposite is now over here, which is the number 5. And my adjacent is 10. So notice that this ratio is now upside down from what we had it as before. 10 beta. Same concept. I'm trying to isolate this. This is the variable. Just like theta was the variable here, beta is the variable in this one. I can simplify this as a ratio. It's 1/2 or a half or 0.5, however you want to put it into your calculator when you run it through. And then because we're trying to get the variable by itself algebraically, which is our b, we bring tan to the other side. So we work with the tan inverse of 1/2. We'll bring up that scientific calculator again, and let's just change what our input is. So the argument to this is 1/2, and that gives us a very different angle. In this case, it gave us 26.5 roughly. There we go. So our beta, or angle B, is equal to 26.5. And these are all within degrees. And we could have checked that. Technically, as soon as we got this angle, I could have just got the internal angles of a triangle. Yeah, and subtracted from 180. But this is the same process. We wanted to practice using tan. So what we did is we put tan to two different angles, and we noticed that ratio flipped. So depending on what angle we're dealing with, we get a different ratio that we plug into our calculator to solve this. That's quite a bit we did there,